Intrinsic silicon is pure silicon. It is a crystalline material with no impurities. The atoms of the silicon crystal are bonded together by covalent bonds. Take a look at this valency shell of this silicon atom and the other valency shell of another silicon atom. The two electrons here are forming a covalent bond. These two electrons are shared between these two silicon atoms, and the bond are holding these two silicon atoms together. In a similar way, other silicon atoms are bound together by the covalent bonds. This structure can repeat for a big piece of crystal. There's another way to represent the covalent bond like this. The two negative signs here represent the electrons forming the covalent bond and tie the two silicon atoms together. Similarly, for these two silicon atoms, and repeating this pattern, this is a whole piece of the silicon crystal. This is an electronic shell diagram of a silicon atom. It has 3 shells, 1, 2, 3. For electrons with the lowest energy level, it will stay in the innermost shell. For electrons with the highest energy level, it will stay in the outermost shell, or called the valency shell. If the atom is not receiving external energy, these electrons will just stay in the prescribed atomic shell. Atomic shell can be looked upon as energy bands, like this diagram indicated. For the innermost shell, also can call K shell, we say it is the first band, first energy band. Go high up will be the second energy band. And this is corresponding to the middle shell, or called L shell. Go high up will be the valency band, and go high up will be the conduction band. If the silicon atom is not receiving external energy, like what we have just described, the electron will just stay in their prescribed energy band or shells. And for silicon atom, under normal condition, there is almost no, not exactly no, and negligible amount of free electrons is in the conduction band. So under normal circumstances, a piece of silicon crystal won't conduct electricity. However, if the silicon atom is receiving external energy, then electrons in the K shell can be actually jumped to the L shell, or if the energy level is really high enough, it can even jump across 2 energy gap, or even jump 3 energy gap, but that must be very high level of external energy. And what are this external energy? Is usually is heat energy or light energy. And once electrons from the valency band or from other lower band jump to the conduction band, they become free electrons. And free electrons will become electron current if external voltage is applied across to the piece of silicon crystal. This line shows a piece of intrinsic semiconductor receiving external heat energy. Some of the electrons in the valency band can gain enough energy and break away to the conduction band and become free electron. That left behind a vacancy, we call it a hole. A hole and the free electron together, we call it an electron-hole pair. In the case of semiconductor, the energy gap between the valency band and the conduction band are rather large. That's why the number of electron-hole pair is limited. The same concept can be described by covalent bond and valency shells. When an electron in the covalent bond receives enough heat energy, it breaks away, becomes free electrons, and left behind a hole. The covalent bonds can be represented in this manner. When this piece of silicon receives external heat energy, some of the electron will break away from the covalent bond and left behind a hole. So electron-hole pair is created. But when the free electron loses its energy, it will jump back to the nearby hole and recombine with it. The process of creating the electron-hole pair and losing the electron-hole pair are constantly happening when this piece of silicon is being heated up. The message in this slide has actually been discussed in the previous slides. It's about free electrons in intrinsic semiconductors are thermally generated. When a voltage is applied across to a piece of intrinsic semiconductor, the free electron will drift towards the positive terminal of the supply. And the movement of the free electrons is called electron current. This diagram shows the drifting of the free electrons, the red lines here, from the negative terminal drift towards the positive terminal. This line shows in atomic level the movement of the free electron and the holes. This side is the positive terminal of the external supply, and this side is the negative terminal of the external supply. Free electron is thermally generated, and because it is so close to the positive terminal, it will go into the positive terminal. And when the free electron is generated, it leaves a hole in the valency shell here. And because this hole is very close to the positive supply again, it will attract this valency electron to fill it up. So it rises, the valency electron move into the first hole and leave the second hole. And similarly, the valency electron here will try to fill up this second hole and leave the third hole. And this valency electron will move to fill up this third hole and leave the fourth hole. And in the same manner, we will find effectively the electron is moving in this path. This is called the electron current. While the hole is moving away from the positive terminal effectively in this path. This is called the hole current. And lastly, we discuss this. Because the energy gap between the valency band and the conduction band in an intrinsic semiconductor is quite large, so end up you have very limited amount of free electron and holes. So that means there are limited amount of electron and hole currents.